Hello, welcome to my talk. So, knock knock, who's there? Is me. Hey, I'm Aaron Durder. I go by Torch2424 on the internet, mostly Twitter and GitHub. And here are a few things about me. I am the Wasm by example creator and maintainer. What Wasm by example is a bunch of bite-sized examples for getting stuff done in WebAssembly, or Wasm as I'll refer to it in this talk. And it supports multiple languages. It has a TypeScript-like one called AssemblyScript, has Rust, Go, and so on. So if you know any of those languages and want to check it out, check it out. I also created this project called Wasm Boy, which is a Game Boy emulation library written in WebAssembly or for WebAssembly. And I also maintain madewithassembly.com, which is a showcase of projects using WebAssembly. I also make music, like a lot of lo-fi hip-hop. So if you happen to like code and lo-fi hip-hop, there's this mix out there called CodeFi that was released by the AMP team at Google. It currently has 4.7 million views. So if you happen to like listen to lo-fi on YouTube and you listen to code-related ones, you might have heard it. So I just want to throw it out there. I made it. Yeah. And they also work at Fastly on their WebAssembly efforts. So what are we talking about today? So first we'll talk about is WebAssembly, also known as Wasm. WebAssembly is relatively new. It's a portable binary format that runs on the web, both in the browser and the server, and we're going to talk about its relationship to JavaScript. And we'll also be taking a quick look at WASI, which is a system interface for Wasm. And once we talk about WebAssembly, what WebAssembly is and what benefits it has, we'll then talk about some of the awesome upgrades you can implement in your JavaScript projects by replacing those hot paths of JavaScript with WebAssembly, how you can do it today in production. And then we're going to talk about the reverse. So, put in the clutch. Most WebAssembly resources out there will talk about WebAssembly inside of JavaScript. But what about putting JavaScript inside of WebAssembly? And why would you want to do that? And then lastly, we'll be entering the sandbox, which is, without spoiling the point of the talk, I'll say that we're going to show some really cool use cases of this JavaScript inside of WebAssembly in the wild concept. So, yeah. So first, what is WebAssembly? This phone screenshot is from Wasm Summit, which just happened in April. It's the second edition of this WebAssembly conference that I helped run with my colleague Surma, who's a good friend of mine, but you might know them from like Google Chrome developers and things of that sort. But what WebAssembly is, it is a universal low-level bytecode on the web. Because of this, WebAssembly is great for running logic-heavy tasks compared to JavaScript, such as image manipulation, physics for games, and heavy math computations. But why is it great for this? WebAssembly offers predictable performance. JavaScript needs to be parsed, evaluated, and then compiled many times through a just-in-time compiler, or JIT, as I'll refer to it in this talk. And this can get extremely fast or fall off a fast path. But what bytecode offers is more consistently predictable performance that won't fall off a compiled fast path. In Wasm's current state, runtimes will run the bytecode without any interpretation. It just runs straight through, like vroom. So yeah. One more thing about WebAssembly is that it's extremely portable. And let me move my window. Okay, there we go. And when I say portability, what I'm talking about is it's supported by all major browsers, so you can ship it today on any browser. It runs in Node, and so for example, you can run the exact same image transformation compiled to WebAssembly, both on the client and the server, which is really cool. There's some standalone runtimes. Some popular general purpose ones are WasmTime and Wavm. And if you're more into like IoT and constrained devices, Whammer and Wasm 3 can help you out there. And then there's WASI, which is again that WebAssembly system interface we'll be talking about. And it's very bundleable. And what I mean by that is that you can pretty much publish like NPM packages that, NPM is JavaScript, but you can have WebAssembly modules inside of them. So it's actually using WebAssembly underneath the hood, even though it's a JavaScript package. So it's great for package managers. You can throw it in packages, things of that sort. And right now, there's a lot of languages outputting WebAssembly. The most mature three are AssemblyScript, which is a TypeScript-like language to WebAssembly. And when I say TypeScript-like, what I mean is that you can't compile a React app to WebAssembly, but it has some really nice tooling that's very JavaScript-like, such as Aspect, which kind of looks like Jest in the unit testing library. And it just feels very at home if you're a JavaScript developer. Another language is Rust, which probably has the best tooling right now. It's extremely mature in its WebAssembly implementation. And another language is Inscription, which is a toolchain for C. What it is, it's super mature. It evolved from ASM.js, which is kind of like a typed JavaScript thing that existed in the past, which WebAssembly kind of came out of. But what Inscription does is it turns C into WebAssembly. But kind of a elephant in the room here is that JavaScript as of today cannot be compiled to WebAssembly. JavaScript is a dynamically typed interpreted language, but WebAssembly really likes these statically typed compiled languages. But there's tons of tooling in the WebAssembly ecosystem that JS to Wasm bridge a lot easier, such as Wasm Bindgen and Rust. ASBind and AssemblyScript, which I maintain, and MBind and MScriptin. And I know this is ironic because we're talking about JavaScript in WebAssembly, but we'll cover where this comes in later. Next, another nice property of WebAssembly is that it has this concept of linear memory, which is essentially, does a TLDR, means that you get like a huge heap or array that you can write to between both WebAssembly and JavaScript, kind of like a bridge they can talk to each other over, which makes this extremely easy to sandbox because it's just one heap that they both share. And that way, multiple Wasm modules won't write over each other's memory. So if you run multiple Wasm modules, they all get their own little linear memories to play with. And this is really good for security because it means everything's all sandboxed, so you don't have to worry about it like escalating out and stuff like that. And speaking of escalating, what's nice about WebAssembly is that it relies on a capability-based security or host call system. And what a host call essentially is a function that you can pretty much pass to WebAssembly. You can import to WebAssembly. So what's nice about this is that WebAssembly only has access to like the host or the JavaScript functions if we're using JavaScript as our host or runtime environment, but you provide it. So WebAssembly can only really just run computations, and it can't really do anything that the host would allow it to do unless you give it explicit access, like, yes, you can do this, or I will do this on your behalf for you, WebAssembly. Otherwise, it just can't do it, which is really, really nice for security. And now that we understand some of these WebAssembly fundamentals, what is that WASI? I mentioned like 3 times already. What is this system interface for Wasm? What WASI is, it is again system interface, but it's a standardized set of system calls or other operations that allow for interacting with system resources. So things like file systems, randomness, time, and hopefully eventually things like networking and devices. You can kind of think of WASI like the web API, or the equivalent of the web APIs for JavaScript in the browser. So things like fetch and gamepad API, those give us like access to like special things that the browser kind of does on our behalf. WASI is kind of like the web APIs, except on the server for WebAssembly. And these system calls that WASI pretty much is a standardized set of can be implemented by these Wasm runtimes. So some standalone Wasm runtimes implement them natively, such as Wasm time allows you, to run Wasm files, and you can give it explicit access to file system directories that it can, your WebAssembly module can then talk to and create and stuff. Essentially what Wasm time is doing is, again, running these host calls on behalf of the module. So when WebAssembly says, hey, go create this file, Wasm time's like, all right, bet, I'll go do that for you. And then it continues executing the Wasm. So it's as if the WebAssembly created it. But JS runtimes like node.js and Dino also will, if you run WebAssembly there and you import WASI to it, node.js and Dino will do these operations for it on the WebAssembly module's behalf and stuff. Browsers don't currently implement WASI, and browsers could possibly implement WASI on top of existing web APIs, but for now, there's a bunch of various polyfills. So if you want for some reason to run, not for some reason, but if you want to run WASI in the browser, there's polyfills out there to help you out. And this is all really amazing, this whole WASI thing, because essentially you can get all of those like WebAssembly benefits of like performant modules that are sandboxed by linear memory, but then also still have access to those host functions and resources, but only the ones that you grant it, on top of a standardized set of system calls. It's just, a really great like chef's kiss, like, yes. You know what I mean? It's like all the benefits of Wasm with controlled access to host and system calls, which is really cool. So now that we understand all these benefits of Wasm, let's take a look at some of the use cases of WebAssembly inside of JS. So one of my favorite case studies, or kind of like, articles about this, is by Marcel Dwin. It is an article documenting their experience of moving their application, which is Micreo, a storytelling platform, so kind of like a storyboarding type thing, from JavaScript only to JavaScript and WebAssembly using AssemblyScript. The first thing I want to highlight is they got a drastic code size difference. They were able to shave off 73 kilobytes of their application, and their new application is now 0.7x size of the original application, so it's like 30% smaller. They also highlighted CPU usages. They are now using 65% less CPU for their performance-intensive task, which is really awesome because now you can assume things that their application is a lot more snappy and a lot less draining on their user's battery life, either laptop, phone, mobile, whatever it may be. And I also have my own article highlighting the improvements of WebAssembly can have on your JavaScript applications. I have a project, again, that Wasm Boy, the Game Boy emulation library, I had written for WebAssembly, but I was able to compile WebAssembly with the AssemblyScript compiler and then JavaScript with the TypeScript compiler. So again, because that AssemblyScript language is so TypeScript-like, you can run it through both its own compiler and the TypeScript one if you like kind of play with it weird a little bit. So essentially this means you can have the exact same source code, but then output it in these both WebAssembly and JavaScript, and then you can do things like run and record the runtime performance. And what I saw was about a 30% increase in performance for WebAssembly on desktop Chrome. But the most interesting thing for me, and kind of the goal of this benchmark for me, was I noticed that the less powerful your device got, the bigger the performance gap got. So for example, I noticed a 60% increase in performance on budget Android devices. So like an additional 30% of a performance delta. WebAssembly is faster than JavaScript for these CPU intensive high performance tasks like an emulator would have. And another thing is, again, talking about that code portability of WebAssembly, it can happen across multiple platforms. So Google Earth has a talk for WebAssembly SF. They have a great YouTube channel, tons of resources on there. And what they do is they compile their Emscripten or their C++ code base with Emscripten to WebAssembly. And that way they can have one code base and then run WebAssembly on their web app, but also link that same functionality into their mobile apps. So you don't have to maintain two separate code bases, like all the same one that just outputs where it needs to go, which is really cool, very portable. And another amazing ability we get from WebAssembly is kind of like, I feel like it's not talked about a lot, but feature polyfilling. And this is another amazing talk given by Brian Vibber at WebAssembly Summit 2020. Brian gave a talk from their work at Wikimedia. And kind of the problem here was that due to various patent licenses on different media formats, Wikimedia had to use a more open media format. I think it was Ogtheora. However, not all browsers support these various different media formats. Therefore, Wikimedia had to turn to WebAssembly to decode this video format that they wanted to use. And what they did is they ended up building their own custom video player to polyfill the unsupported formats that browsers didn't currently decode or support. So yeah, essentially they didn't have to wait for the Web API to catch up for these different video formats. They could have just wrote something intensive like a video decoder that a Web API normally would handle for you in WebAssembly and got pretty decent performance out of it, and they liked it. And there's a lot more. So these are just some of my personal favorite use cases, but I maintain a website called madewithassembly.com. So if you're looking for WebAssembly projects and are interested in different use cases, check out this website. And now that we've done a quick crash course on all the awesomeness of WebAssembly in JS, my bad for hitting the mic, let's shift into reverse and talk about JS and Wasm. So to answer this, I think it's best we address the elephant in the room. Will WebAssembly kill JavaScript? Ooh. A common rumor you will hear or may already be thinking is WebAssembly could be the death of JavaScript. It's faster, more portable, runs in browsers, etc. It's a valid question to have, and it is a little scary, but I have good news. WebAssembly is not here to kill JavaScript. It was explicitly designed to complement JavaScript. It's not here to replace it, and we as web developers, we should take advantage of both of the language's strengths. This quote on the screen is from MDM, which supports the idea of using each language's strengths. Like we mentioned earlier, WebAssembly is great at those CPU-intensive tasks that you want to be portable and run on the web, but it doesn't mean that it does everything JavaScript can do. JavaScript is an entirely different thing. JavaScript's interpreted and dynamically typed, which generally means it's a lot easier for newcomers. JavaScript has decades of design iterations on manipulating UI and the DOM. JavaScript has the largest developer ecosystem, as usually mentioned by the Stack Overflow developer survey. JavaScript has NPM, which is the largest package ecosystem in the world. Tons of developers writing code that we can all build upon. And the ecosystem, JavaScript ecosystem, is probably the lowest barrier of entry of any language ever. And, just highlighting the awesomeness of JavaScript, I wanted to post a picture of the last Cascadia event I spoke at because it was an awesome time. And I think it just, is a part of this amazingness of JavaScript that can't really be imitated by anything else, really. So, the point I'm really trying to draw here is that WebAssembly and JavaScript are designed to excel at different tasks. And speaking of the last slide real quick, thanks for having me that year. I forgot to mention that. Thank you for conference organizers. But WebAssembly and JavaScript are designed to excel at very different tasks. Thus, it makes sense that they won't replace one another. And as engineers and developers, it's up to us to choose the right tool for the job. And as we've displayed here, some of these jobs require multiple tools. Now that we have WebAssembly, we can rewrite our CPU-heavy JavaScript into WebAssembly. And bonus points, if you stick WebAssembly in a web worker, you get really fast parallel execution in your web apps. So yeah, then we get these really powerful web applications. But are there other use cases where we kind of have this concept of multiple tools, right? What if there was a job where we needed the benefits of WebAssembly, such as portability to run on multiple platforms, security, and performance, but we also wanted those benefits of JavaScript, like that amazing ecosystem. And honestly, even if we didn't have all of NPM, but at least some of those NPM packages that work on both browser and Node, and folks could use existing JS tooling to build their stuff, or even learn from existing JavaScript articles on how to console.log and things like that. And the ease of use of new developers, what if we wanted all those things? Well, it's kind of too bad because JavaScript can't compile to WebAssembly. JavaScript is a dynamically typed interpreted language. Wasm is statically typed, Wasm only likes statically typed compiled languages as of today. So AssemblyScript is our closest bet. And AssemblyScript does share a lot of the tooling with JavaScript, but its library ecosystem, it's its own thing. And as of today, though, if you wanted like a JavaScript-like language to compile to WebAssembly, you wanted like the full performance of WebAssembly, you kind of have to use AssemblyScript. But we could compile a language runtime to WebAssembly, and JavaScript is a language that uses a runtime. So before we dive into this, let's be completely clear. The best JavaScript performance you're going to get is a JS engine that is compiled for your platform in a web browser or whatever it may be, web browser platform. You won't magically get faster JS or magically have the ability to run like WebAssembly fast JS, especially not faster than a JS engine in Wasm. But this still does open amazing doors. Let's look at a use case for this idea. Let's say we have this platform, this example platform, and we want to allow developers to build, like third-party developers to build on it. What can we do to deliver on performance and developer experience while making sure our platform is flexible and secure? Well, this is a really hard problem to solve. There's a lot of concerns here, like security. How do we avoid bad users from using the platform? Portability. We hope our solution will work on both the web and native or whatever many platforms we want to support. There's some constraints too, because some platforms like iOS and game consoles, they don't allow you to do just-in-time compilation. So you have to interpret the language. Performance, we want to make sure you can have more than one plugin. Our apps are just not going to get suddenly slow when they add too much plugins and things. And the ecosystem, you want to make sure our developers building our platform have tons of resources to learn the language and build powerful apps. Well, WebAssembly and JavaScript have a lot of great features that help solve this problem. Example, WebAssembly solves that platform security thing with the linear memory and the capabilities. Third-party devs can escalate out and abuse the platform, or like our host provider or whatever it may be. WebAssembly is portable across platforms, so we can run WebAssembly in the browser or Node, and we can even embed these standalone Wasm runtimes in our native apps to run this WebAssembly code. And WebAssembly, as of today, yet can't generate JIT code, which is kind of this helps because we can run Wasm on devices that don't allow that JIT compilation, such as like iOS and game consoles, like I just mentioned. And WebAssembly is really fast, so take this with a grain of salt. It's about 30% slower than native, depending on the use case and things of that sort. But even then, compared to alternatives, like 30% slower than native is like not bad compared to other alternatives. So that's great. Again, grain of salt use cases. It's all depending. Numbers are depending. But and then on top of all that, all those WebAssembly benefits, we also get the amazing developer ecosystem of JavaScript, which means we can actually explore this plugin use case that we have right now. So let's enter the sandbox. And what essentially I want to show you is some awesome use cases of JavaScript inside a WebAssembly compiled JS engine, currently in the wild in production today. So starting off with browser use cases, it's probably one of the first ones I've seen of JavaScript in Wasm, but PS PDF Kit has a web-based PDF engine. And the thing about PDFs is that some PDF files allow for JavaScript to be run inside the PDF for things like input validation and things. But PDF Kit uses the duct tape JS engine to securely run JS. What this allows is the JS execution in the PDF can't escalate out and mess with window or any global properties and stuff, because when you do an eval, JavaScript just does whatever it wants. But when you have a sandbox instead of WebAssembly, it can't escalate out. It can't, we only has access to what we give it. So it can't call global functions unless we provide it to that WebAssembly module to call our JavaScript executions environment, which it can't. So that's really great for security and doing this third-party logic execution without having to worry about it, taking over the browser or something. And there's even other alternative JS engines to duct tape that compile to WebAssembly. Another one of another really cool one is QuickJS. It's a JS engine written by Fabrice Ballard. Fabrice wrote FFmpeg, the video encoding thing, and QEMU or Kemu, I don't know how to say it, but it's really cool. Both amazing, mind-blowing projects. But it's also a lightweight embeddable JS engine with some really impressive performance characteristics. QuickJS compiled to Wasm is already being used in production today by Figma, and in this article Figma highlights and they call out how they switched from QuickJS for their plugin system, which gave them some really quick security wins with the sandbox execution they were using previously, and it patched out some security vulnerabilities in their old JS execution really fast, and they did it all in 11 days. So that whole moving to this new solution didn't take them a long time. So hats off to them, because I'm sure there's a lot of hard work that went into that, but also just shows that WebAssembly, you can kind of get up and running with it pretty fast. And what's even more awesome is that multiple folks in the community have quick.js ports to WASI. So if you wanted to use quick.js in a WASI context, thinking like Wasm outside of the browser, something like that, then you can get started here. One of the contributors to this particular repo is a colleague of mine, Frank Dennis, who is the author of Live Sodium, if you're familiar. But yeah, check it out. And awesome. So now that we know some of the pre-existing lightweight JS engines that we can compile to WebAssembly or WASI and run some JS, but what if we want to do more intense use cases than what I just talked about? So more intense than custom input validation or just data manipulation. What if we wanted to allow users to build entire applications in JavaScript that run inside of a WebAssembly compiled JS engine? Could we do JS on Wasm even better? Are there any other performance improvements we can offer, or could we even use the highly optimized browser JavaScript engine inside of WebAssembly? Well, someone else asked this. The Bytecode Alliance did. The Bytecode Alliance is a group of companies investing in WebAssembly and WASI. Companies like Fastly, Mozilla, Intel, Microsoft, and Google. I work at Fastly, just as I mentioned earlier, just to get that out there. But they are working together to help bring a shared vision of secure by default WebAssembly and Wasm, Wasm and WASI, which will greatly help in this idea of running untrusted third-party code. So Lynn Clark is an awesome colleague of mine, and they're one of the active members in the Bytecode Alliance, and they recently shared an awesome article on Bytecode Alliance's efforts towards JavaScript on Wasm. And the real exciting bit is that the Bytecode Alliance got SpiderMonkey on WebAssembly. So if you're not familiar, SpiderMonkey is the JS engine used in Firefox. So we know it's a battle-tested, everyday used, production-ready JS engine. And the work of getting SpiderMonkey to Wasm was done by my colleague Chris Fallon and fully upstreamed in collaboration with Mozilla and Igalia. So some of you might be saying, hey, doesn't SpiderMonkey use a just-in-time compiler just like most browser engines? And didn't you say we can't just-in-time compile in WebAssembly? So yes, unfortunately, this SpiderMonkey Wasm does not use a JIT. However, we are using SpiderMonkey's amazing JS interpreter, and there are some things you can do to help those execution times. So Bytecode and clients came up with some really clever optimizations, and let's cover the solution they came up with. So applications in JS runtimes usually have two phases: initialization and runtime. Initialization of the runtime is usually pretty quick, like the actual getting the runtime ready, but the application initialization could take a while usually. And the initialization is usually the phase where the JS engine and Wasm will do things like set up global objects, prepare built-in functions, etc. And a JS application might do things like define constants, register routes, so on and so forth. And the key insight here is that what matters really is how long something takes to run end to end. What JIT compilation does is that it makes things faster end to end by optimizing all the steps over and over and over. But what if we just took out some of those steps and we just have less work to do end to end? So we built a solution for that. Nick Fitzgerald is an awesome colleague of mine. Just as a heads up, they're really good at Rocket League and they make some really amazing hip hop beats. But they built a really cool tool called Wiser. And what this does is allows moving any Wasm module startup logic to build time. So in our case, instead of running the initialization phase when we start running code, we can move that to build time and immediately just start the runtime phase. So we don't have to worry about setting things up. We just start running. And you can learn more about Nick and Wiser at their Wasm Summit 2021 talk on YouTube. And honestly, this is surprisingly, but Wiser works well enough for most JS on Wasm use cases. And that's pretty much the punchline of the JS on Wasm story from the Bytecode Alliance perspective. And let me illustrate what those use cases are. The use cases that work great for this are short-running, CPU-friendly tasks. Because we can move the initialization build to build time, Wiser plus SpiderMonkey immediately starts execution on the interpreter. And a JIT normally wouldn't optimize this early because there's no hot code yet. However, the longer it runs, the more obvious that there's no JIT on Wiser. And a JIT will continue improving over time until it intercepts and blows past the solution. There are some plans of surrounding around ahead of time JS compilation that we have, or the Bytecode Alliance has, and the blog post I mentioned, you can read it and find out there. And this will help with this use case in the future. But we got some dope solutions on interpreting JS fast on a production-ready JS engine, which can be improved over time, like we mentioned those future solutions. So what can we do with this? Well, this makes a perfect storm for a JS serverless environment. At Fastly, I work on the Wasm team building out their SDKs for different languages for their the serverless product compute at edge. Using our existing WebAssembly execution environment at the edge, we are able to provide a fast JavaScript compute environment on top of Fastly's edge network. And thankfully, we were able to open source our JS bundler / runtime thing that takes your JS code, sticks it in SpiderMonkey, so on and so forth. And Till Schreidenreich is the lead maintainer on this currently, so shout out to them. And lastly, Till and I published all this goodness onto an NPM module. So this sounds like something you want to try, this being the JS serverless execution environment at the edge. Check out all the benefits of Kubernetes Edge on the Fastly website, such as like microsecond cold starts and stuff that are like really fast and help your users on the Edge network. And after signing up, head over to the JS documentation, the Fastly developer hood, get started. And you don't even need to sign up, honestly, because you could just use the Fastly CLI, Fastly Compute Serve, and you can see the link. I'll share the slides after. And I'll be wrapping up this talk on a cliffhanger. So as we mentioned before, we can compile any language's runtime to Wasm. So like, what about something like Python or Lua? You know what I mean? So it's something I'll be looking into, and I hope you will be too. So in conclusion, here are my main points. Wasm is super exciting, opens lots of doors on the web, both in the browser and how we architect our applications end to end. Wasm and JavaScript are different tools. So Wasm is great for CPU intensive and portable tasks. JavaScript is great for DOM manipulation, being easy to use, an amazing ecosystem. Wasm inside of JavaScript is great for web apps. Replacing those JS hot paths with Wasm can greatly improve your app performance or allow architecting entirely new, very performant dependent heavy apps. And JS and Wasm is just a really cool space. The other way around is a really cool space because it unlocks all types of doors for new use cases, one of them being able to sandbox and securely and performantly run third-party code. So with that, thank you very much. Thank you to my team at Fastly. Thank you, the Wasm team especially. I usually name everyone out, but I especially want to thank and shout out the Execute D team, where they write the actual daemon that gets all of our serverless stuff running on the servers. Really happy to get to work with these people every day. Thank you, conference organizers, for having me, especially for a second time. And thank you for watching. Please reach out to me here, in the event, or over on Twitter. Let's continue this discussion. Thank you very much, and enjoy the conference.
And thank you. We're back. And Aaron, that was an amazing talk, and it is spawned just a ton of conversation on your AMA channel. I want to tell everybody, if you want to go deeper on this, go to Aaron's AMA channel, because there's a lot of great questions there, and he has been answering them. But there are a couple that I have here that we want to ask you. The first one is actually one you wanted to be asked, which is, why is your name Torch2424?
Yeah, so I always like to start off with something funny. The reason why is because I've been on the internet since I was like 6. And when I was 6, I had an imaginary friend dragon named Torch. And my favorite number is 24. My kid brain was like, why not just do it twice? It'd be double cool.
And it is, definitely. All right, so here's a question that came in through the Q&A gizmo. What is a CPU intensive task by your standards that helps you determine where Wasm makes sense to improve performance?
Definitely. So really you can think of things like, so you can think of things like physics, like any heavy math computations. Pretty much if you're like iterating over some type of data in a loop, it's probably kind of heavy in terms of like working out the CPU load. So things like parsing JSON, things of that sort. Or you can honestly, like, I wouldn't want to go all the way there, but you can kind of think of like, if something doesn't exist on the browser right now, like you can think like maybe something like Photoshop. Why isn't that there yet? Why isn't like, maybe Call of Duty or some big name game not there yet? It's probably because it's there's a lot of CPU intensive tasks in there. So if you're thinking of like, okay, I have a ton of data, or I'm trying to build this like high performance application, things like WebAssembly are great for that and kind of solve that problem that JavaScript was kind of struggling to do before.
Oh, cool. And so, you were giving us a lot of tips about using WebAssembly. Now, a good question is, let's say I'm a total noob at WebAssembly. How do I get started? Where do I go to learn to write my first hello world and sort of build from there?
Yeah, definitely. Yeah. So this talk was a little bit more of the advanced side of like WebAssembly, I will admit, with like a slight introduction. But if you're like brand new, I maintain a website called wasmbyexample.dev, which I can post a link to. And it has like in multiple languages, either assembly script if you're a JavaScript developer, like you probably are watching this conference, or if you want to try Rust or C or even TinyGo. We got TinyGo support on there. You can go ahead and try Hello Worlds out in a language that you're comfortable with. And it goes all the way from like Hello World, I think, to like building your first kind of cool graphical-y type app and playing around with WASI as well. So yeah, I'd suggest wasmbyexample.dev.
All right. And that is wasmbyexample.dev?
Yeah.
All right. All right. Thank you so much, Aaron. Now I'm going to throw this over to our fearless leader, Carter, who has some announcements for y'all before he sends you off to lunch.